We're trying to get to the point where we can use experimental measurements to calculate the coupling, the strength of the weak force. How does it connect two different states? So first I want to talk a little bit about what does it mean to connect two states. Where does that word coupling come from? And so we can start with our particle in the box and our first wave function. That's the smallest curvature you can have, right? You can't have any less curvature than that, because then it would stick out past the barrier, and we know those walls are, that force on the two sides are strong enough to keep it in there. But we can't get more kinetic energy. That's more kinetic energy. And then one of the things you're really interested in, one of the things that we're first trying to do with the original quantum theory was how do electrons make transitions. One of the things they really wanted to understand was the specific lines that came out of all the elements. They'd already know that if you made an element glow, you could see the lines in it. And they interpreted that as electrons going back and forth. They wanted to understand why they went between those and not some others. One perspective is this idea of wave functions and integrals and so on. There's another perspective that has to do with matrices and multiplying them, and that's a perfectly fine way to do it. This is the way you're going to learn in your quantum class. If you took a class in quantum mechanics here, you found wave functions, you solved it for a particle in a box and a hydrogen atom and all that, right? If you haven't, that's what you have to look forward to. So in that picture, that wave function picture, this is basically due to Schrodinger. That picture says that if I want to know whether or not we don't need a 3. I would normally have to do that over 3 dimensions, but we live in a one-dimensional world in this class, so. I calculate that by looking at what are my initial function, my final function, and then doing that integral. So tell me what happens when I integrate those two functions. Multiply them together, do that integral in your head, and tell me what you get. And I'm not asking you to integrate sines and cosines. I'm trying to just get you to remember, what is an integral for real?
The addition of many small pieces.
That's a way to think about it. And if I'm plotting a function, I'm multiplying the height times the width and adding them up. So what do I have? Height times width?
An area.
Yeah, it's an area, right? And if I add them all up, that's the total area under there. And so you look at that and you say, yeah, there's definitely an area under bluey, not under red. But look, if I multiply these two together, this looks the same as this looks the same as that, with one exception. The left side looks the same as the right side, with one exception. What's the one difference between them?
Yeah, negative area.
Minus sign, right? And that's it. So what happens when I add those two areas, quote unquote? I put quotes around the word area because you're not used to a negative area, right? Nobody's ever seen a house for sale with a negative square footage. But we definitely get negative areas here. And what do you get if you add all those together?
0.
You get 0, right? I got just as much plus as minus. If you go through the work, right, integrate half a cosine times one full sine oscillation, you get 0. The fancy word for that is orthogonal. Where else have you heard the word orthogonal? Go.
I wasn't gonna talk about orthogonal.
Oh,
I was
okay.
gonna ask about those graphs.
Well, fine, you talk.
So, you're saying when you add the area under the curve of those graphs, you get 0?
Yeah, and I'm multiplying them together. Keep in mind that I'm multiplying them together. So this will look something like,
Oh,
you know,
okay.
that, and then that on the other side.
Mm-hmm.
I'm not saying that this area plus this area is 0. I'm saying those two multiplied together
Give you 0.
give me the same area on the left as on the right with a minus sign in front.
Mm-hmm.
Is that better? That helps clarify what
Yeah.
bugging you, or? No?
So the area of the second one, when you integrate it, it's 0, and 0 times the initial one is 0. 0 times the area of the initial
Yeah,
is
the
0.
times is what's freaking me out. So let's go ahead and do that just a little bit. So here I got 0 times 0. Here I got 0 times something.
Mm-hmm.
Here that's a line times a line, so it's kind of quadratic. It goes to here, but now it goes to negative, and because over here I'm 0 times 0, because of the symmetry of that, it's going to look the same on both sides.
Okay.
That's the product. And I'm sure I didn't do it very well, but get on Desmos and plot that function, and the product.
Mm-hmm.
That's how I like to do it. I love Desmos. So, but whatever your favorite is, right? Your favorite way of visualizing functions, I think.
I like those two.
Yeah,
It's easy.
very much. So I have positive area here, I have negative area here. When I add those together, I get 0. So you would say those two are orthogonal, and you would say that they are not coupled. And what that means quantum mechanically is, as they would say in New Hampshire, you can't get there from here. These two functions, these states do not overlap. Therefore, you may not go from one to the other. That's the rule. And apparently, whether the universe does math, we don't know, but whatever the universe does, it's like the math of integrating these functions. So, if I can't get from one to the other, then I need some way to connect them. I'm going to have to change one of them. And the way you change it is you operate on it. You do something to it. One of the things you can do, and this is what, I'm not going to write it, but this is what, in this section on page 1613, it's kind of what Iceberg talks about. I'm looking at, basically if you look at the equation near the bottom, he's got an electric dipole term. That's an electric force.
Equation 1613, or?
Yeah, right there, that one
Yeah.
down there at the bottom. Yeah, we're going to talk about that one. But he's likening that. So what happens? You have an electrostatic connection. E times R is an electric dipole, like you did in 222. So it's an electric dipole. What that does is it changes this state. It shifts it, makes it a different function. You operate on it, it becomes a different function, and when you do that, maybe now the integral's not 0. And if the integral's not 0, then you can make a transition. That's called coupling. And so what they do is, in his development, he talks about simply putting in that function beta. What that beta does is it changes that initial function into something that overlaps with that final function. Now you can make a transition. Now you can change from one state to the other. Where a lot of that comes from is, you may have heard that if you put a particle in the ground state, it stays there. If you put it in an upper state, it doesn't stay. But that tells you there's something else that you have not included. Because when you find these states, when I find the ground state of the hydrogen atom and that first excited state of the hydrogen atom, when I find those are all what are called stationary states. And stationary means exactly what it says, stationary. They don't change. They don't move from them. You may have heard that they can't have any other energies. That's not true. They can have any energy they want, but if they have one of these special ones, and we'll talk more about why they're so special. If you have one of these special ones, they stay there. They're kind of like an infant. Put them someplace, they're there when you come back. Here, you put an electron in one of these energy states, they stay there. Somewhere else, they don't, right? But it can have any energy, it won't stay there if it has one of those. So these are stationary, stable, and so on. But even this one is not completely stationary, it's got some place to be. It can go down from there, and so it does. But if it does that, it means you left something out. And that's a big part of what they try to figure out is what did you leave out that makes things fall. That's a separate conversation that we don't have to get into. For now, if you're going to make a transition from an initial state to a final state, you need something that connects them. Another word for connecting is coupling. We call that the coupling constant. That's that beta. And I'm going to wave my hands so wildly there's going to be a breeze. And we will get to what we're going to try to use to calculate that. It kind of starts with that equation that I showed you, and I sort of identified the different parts. We're going to wave our hands some more. They add, so where's a good place to be? I mean, maybe equation 937 on page 114 in Dunlap, or equation 1617 on page 570 in Iceberg. I don't know why I can never remember the name. They added the term F, and again, in my hand wavy way, that F is an attempt to add in the Coulomb forces that are involved there. So when you start off with a neutron and you go to a proton plus an electron, you now have a Coulomb interaction there that complicates things. And I'm not even going to pretend to try to calculate it. Just know that better men than me have done it. Better people than me have done it. That's what that F is. And that F is something you look up. Different interactions happen at a different half-life, a different time, 1 over e time. This is actually the 1 over e time. Or a different half-life, and I'm going to do one from Dunlap and one from Iceberg, just to give you two, right? And also indicate a little bit of the difference in the notation. So you look this up on that table. You look that up for the reaction in question, and then you can calculate. That gives you a way to calculate beta. If you look at equation 9.43 in Dunlap, or, well, he actually does example 16.4 in Iceberg. He does an example and goes through and calculates beta. No, he doesn't do it there. Example 16.4 and I guess 16.5 together, he calculates beta. And I'm going to sort of talk my way through that. Before we get there, I'm going to talk about something about these wave functions and what must be true about them. We're not going to do a three-dimensional integral, but I'm going to talk about the three-dimensional integral. And basically, he has an m prime, that is the integral of the wave function when you have z up or down by 1, when you start with z. So all we're looking at is what happens to the proton. And you've either converted a proton to a neutron or a neutron to a proton. You've done beta decay. Now it is a three-dimensional integral, and we're not gonna do it. We're just gonna talk about it. Well, let's imagine hypothetically, and just for the sake of argument, that psi z plus or minus 1 has opposite parity from psi z. Who remembers what parity is? We were talking about in one dimension, about whether it was an even or odd function. I do a more detailed discussion of parity, but I guess I do it later. So we're gonna come back to that. When I talk, I'm gonna talk about parity decay, and I think I talked about it there. In three dimensions, what it means, they talk about it as a mirror image, and I'm not sure I understand that. Because when you look at the parity of these things, for one dimension, you look at the left and the right, x to minus x, right? But you also care about y to minus y, and z to minus z. In other words, you're taking the function and you're reflecting across to the opposite point through the origin. So you're reflecting, but you're reflecting 3 times, I guess, or at least twice. Do you understand how a parity operation is a mirror thing? I understand how it is in one dimension, but I don't understand it here because this is a 3-dimensional parity operator.
I always have trouble visualizing it, but I just kind of think of a sphere and just kind of go like that.
You do that, but you have to do it the other way. So if I do this in the mirror, it's over there. But a parity operation would take this hand down to here, and it would take my front to the back, my hand to the bottom, and across to the other side. So it's not a mirror. Somebody, if you guys can figure it out, if the mirror is anything more than just something they tell people in Scientific American, let me know. But I'm with you that I don't visualize it that well. But if they have opposite parity, tell me what's going to happen. I'm integrating from x to minus x, from y to minus y, and from z to minus z, right? I'm plus and minus on all 3 axes. What does it mean to have opposite parity? When I do, just think about x for now, and just keep in the back of your mind that's happening with all 3 dimensions.
One is an even function and one is an odd function.
Okay. And if they have opposite parity, what they mean is that it's a minus sign, right? Well, what happens if this function has the same magnitude and the opposite sign for minus x as it does for positive x? What's going to happen when I integrate it?
You get 0.
I'm going to get 0. And if it's the same for y, what am I going to get? And for z, what am I going to get?
0.
So what do I have here? I have 2 opposite parity functions. And so this product, if they have opposite parity, one's going to be plus and one's going to be minus, or vice versa. And the net effect is I'm going to get 0 integral for my matrix element. What if they have the same parity? What happens if they have the same parity? And actually, I kind of said that a little bit. That means this is a plus. Now what happens? It's the same for the left and the right side. What do I get?
Would it just be 1?
Something, right? I can normalize it to be 1 if I want to, but I'm going to get a not 0 number. So, again, if these have the same parity, they're both going to be pluses when I go from plus x to minus x, or they're both going to be negative when I go from plus x to minus x. So the product, they don't have to all both be even, but they have to have the same parity. The product will have even parity if they have the same parity. They'll both be plus or both be minus. That's my understanding.
I think I figured it out.
Go.
So if you make the x and y coordinates negative, you're just rotating. But then to make the z negative as well, that's the mirror image.
X and, okay, if you invert X and Y, you're saying that's a rotation?
Yeah, so.
And
X
then a
Y
rotation
is
plus a reflection,
this,
okay.
And then I have to like,
So you're saying it's a rotation plus a reflection?
Right.
Okay, now let me think about that some. That I believe now, but that, again, it's not just a mirror image, it's a mirror image plus a 360, what is that? 180 rotation, whatever that's called. So, if they have the same parity, this gives me a number. If they have opposite parity, it gives me 0. And that means I cannot connect them. Oh, one thing they do, and again, I don't follow this expression completely, but they do something you don't typically do, is they pull that out here. Both authors do that. And I don't know if that's because it's spatially independent, or if it's infinitesimal, or it doesn't depend on X, or, again, I don't follow their discussion very well. They pull it out of there. So now all I need to know is properties of my initial and final functions. So a couple of things have to happen. My initial nuclear state and my final nuclear state have to have the same parity. Parity must be conserved. The other thing that has to be conserved is the angular momentum, because if they have different angular momentum, these are orthogonal. And again, I'm not going to tell you any more than that. Just know that if you're in a different state, you're in an orthogonal state. So the nucleus has to have the same angular momentum. Angular momentum has to be conserved, and they have to be in the same parity. Otherwise, then it will winds up giving you 0. So, as an example of this, one of the beta decays would be my nuclear state of 2 neutrons and a proton going to a final state of 1 neutron and 2 protons. Neutrons, protons. That's hydrogen 3 going to helium 3. The only difference between those is the Coulomb interaction, and so I calculated that just to see how big it is. So I calculated the Coulomb interaction from the semi-empirical mass formula, and I got a difference of 1 MeV per c squared. The total mass is something like, I got 2807 MeV per c squared, and a binding energy, and these are all the these are the same calculations we did back in the day. I calculated a binding energy of 8.5 MeV for hydrogen 3 and 7.7 for helium 3. So what that tells me is that this Coulomb interaction is really small compared to the total mass, and it's small but not infinitesimal compared to the binding energy. So that Coulomb interaction may or may not be a trivial element of what goes on. When I wave my hands even more later on, when I do a couple of the calculations and get numbers that are, I don't get the same number for that data. We talked about that the energy was not conserved. Pauli talked about what the neutrino had to be. It can carry energy and momentum. Everybody remembers the neutrino and where it came from. We looked at the energy that was released there, and the electron never had it. In fact, the electron seldom had that energy. It almost always had much less energy. That was the energy spectrum that we looked at. The electron almost never got all the energy that was missing. Some of it was gone. Pauly said it's not gone, it's being carried by this neutrino. So it can carry energy and momentum. Not much of a constraint because virtually everything can carry energy and momentum. Electromagnetic fields can carry energy, particles can carry energy. So that's not a big deal. It's gotta be hard to detect. The reason is nobody's seen it. And so it had to be hard to detect. And it must have spin 1/2. So this neutrino must have spin 1/2. Let's see if we can figure out why. Because in the process there, I have a helium-3, a hydrogen-3 going to a helium-3 plus an electron. That's what's seen, plus this ghost particle. What you find out is this is in the state, the neutron is in J = 0, and the proton is in state 1s ½ Over here, the protons are in J = 0, and the neutron is in 1s ½ But I know the electron has a spin. People made magnetic field measurements of the electron. It's also got spin 1/2. So I've got a spin 1/2, J = 1/2 here. I've got a spin 1/2, and I need to get total J = 1/2. And you can't get there from here. Does everybody see that? Look carefully at that and tell me why you can't get spin 1/2 out of my helium-3 and my electron, no matter how they're oriented.
Because it's 1/2 for
I got
the,
J 1/2 here, I got J 1/2 here. They either add up and give you 1, or they cancel and give you 0, but they can't give you a half. So, whatever this is, it's likewise gotta have spin 1/2. And now I've got three spins of 1/2 that I can pair somehow and get them together. That idea that these combine together to give you either 0 or 1 is gonna be relevant. And that can happen, right? If these combine to give you 0, they combine with that 1/2 to give you 1/2. That's okay. How can a spin 1 particle combine with a 1/2 particle to give you 1/2?
one minus 1/2.
Yeah, it's no more complicated than that, right? They combine in a way where they tend to cancel. They tend to spin in the opposite direction, if you believe these are little things spinning. So it would have made sense to do that for tritium, but I guess I don't know if I couldn't find a number, if I just spaced it off, but here's where we are. We have this new particle, this neutrino, that comes along with it, and that conserves angular momentum and energy, and that's why you look for it. And then next in my notes, I calculate this one. I just calculate the neutron, the free neutron decay. That's the one I decided to calculate. And there's no reason not to do the tritium to helium-3, but maybe that'd be a good one to work on someday. if you know what I'm saying.
I don't follow your meaning.
You don't follow.
Elaborate?
And see where I'm headed with that? So, we have, let me go ahead and write where I'm starting, just so you know, 1670 says that the rate, which is 1 over the lifetime, this is the 1 over E lifetime, there's gonna be a log 2 popping up out of nowhere, is a bunch of constants, m to the 5th, c to the 4th, 2 pi cubed, h bar to the 7th. Here's my weak energy coupling constant. And then my matrix elements. And that F, which we look up on the table, and I'll talk about how to get that. So I need the maximum electron energy, and for a neutron decay, I got 0.78 mega electron volts. For the half-life, I used 1,000 seconds. It's actually closer to a little under 900. This gives me a ballpark figure. This is not the source of my problem. There is, however, an interesting, if you look up the neutron lifetime puzzle, it's actually what they call it. You Google that, you find out that there is a tension, a scientific tension between the 2 different measurements of that lifetime. And they have been, for a while, the difference was here and the error bars were here. And I said, okay, nobody's worried, right? Because the errors, you just keep working, eventually they're going to come together. Well, they have come together, and now the error bars are much, much less than the difference. So you got these 2 techniques of measuring that lifetime. And it's like around 887, I think, 878. It differed by like 10 seconds. But the error bars are small enough that that's a big deal now. So that's a point of contention. So if I go to figure 1613 and look up, find 0.8 mega electron volts on the horizontal axis and go up until I see where it crosses, I find that this number tells me that the log of F, and I got around 0.4. I also read it off of Dunlap, and it's not too bad. But that's a weird reading off of a graph, and so that may be a part of my issue here. Because to get that, to get what F is, I got to take 10 to the 0.4. Wow. And I got about 2.5. So that means FT is, which is going to be that F times that T, is, well, I get 3570. What did I do? That times that. Oh, I know what I did. Who knows what I did? If I take 2.5 times 1,000, I don't get 3570. What did I say this T is? 1 over E time. We talked about that, the difference between the 1 over E time in the exponential decay and the half-life in the exponential decay. They differ by a log of 2, so there ought to be a log of 2 in there. I didn't write it down in my notes. I wrote it on the Dunlap example though. So there's a log 2 lurking around. And 2.5 times 1,000 divided by log 2 should give you 3570. So beta squared is 2 pi cubed h bar to the 7th and then minus 30 kilograms to the 5th, 3 times 10 to the 8th meters per second to the 4th times ft times, and I think I just used 1 for this matrix element. That's as big as it can get, and so it can only go down from there. So this is likely an overestimate. An underestimate. This denominator can only get smaller. M star is right here. That can only get smaller. So that can only go up from there. So this is a minimum estimate of beta. Because I don't know how to calculate the wave functions of a neutron and a proton in beta decay. Who wants to do those units? Yeah, I wasn't happy about it either. But you should definitely do them. If I did it right, I get joules squared meters to the 6th. And I get 3 times 10 to the minus 124. For beta, for free neutron decay, I get a coupling constant of 1.7 times 10 to the minus 62 joule meter cubed. That is beta integrated over the volume of whatever this reaction is. If I use the volume, find the average of this over the volume of a neutron. The volume is 10 to the minus 15 meters cubed times 4/3 pi if you want to. And again, I'm just following through his example. You read through his example. That'll help you figure out what's going on. I get beta of roughly 4 times 10 to the minus 18 joules, which is around 26.5, I guess, electron volts. Take a deep breath. Bad air out. Long way to go. Basically, we calculated that beta. He got, when he did his example, he did the tritium to helium-3, and he got, where you at? Oh no. He started it in example 16.4, and then he finished it he gets a much smaller number. What did he get? That's on page, example 16.5. You got a number close to what I got. something on the order of 10 to the minus 62. He gets a fraction of an EV for that. But if we take that 26 EV as the strength of the interaction between these two states, the strength of that interaction that gives rise to the decay, how does that compare with the strong nuclear force? What sort of energies do you talk about when you talk about the strong nuclear force? Mega electron volts, right? Millions of times bigger than that. So that's the sense in which this is truly a weak force. Now, proton-proton interaction, if you look at that, that's also mega electron volts. So the electrostatic interaction between two protons is big compared to that. That gives us that hierarchy I was talking about. The gravitational interaction between them, that's worth doing. Calculate the gravitational force between them and put it in EVs just to see how crazy small it will be. That's a useful exercise, I think. Calculate that gravitational. Now we've got that ordering. And this is sort of the origin of where it comes from.
The gravitational force between a proton and a neutron?
Yeah, put them in the nucleus. All right, two protons gravitationally interacting, nuclearly interacting, and electrically interacting. And proton neutron, you could do the gravitational force of proton neutron if you wanted to. It's not different. You can't do the electrostatic interaction between a neutron and a proton because there isn't one. Well, there's no monopole interaction. So that was my goal in that section. And then I charged you with doing similar calculations. I'll tell you. Decay of bismuth, 83 to 10, to polonium, 82 to 10, and I got beta of 3.0 times 10 to the minus 64 joule meters cubed. And carbon 14 to nitrogen 14. I don't know if I even did this right, but I got beta 4.5 times 10 to the minus 65 joule meters cubed, so very different. Trying to figure out why it might be so weird. I don't know if I came to any conclusions, but if you look at carbon 14, P equals 6, so that's in the 1p 3/2 state, there's two of them. N equals 8, which is the 1p 1/2, but they're paired up. For nitrogen 14, am I doing that right? I'm not. I'll finish that in a second. Where do these 14s need to go?
On the upper right hand.
On the other
side.
side. long as we're doing it, tell me what the rest of them are.
Carbon should be 12.
Well, normally it comes 12, right? But there is a carbon 14, and it
There is.
decays by beta decay, and that's how we date old stuff. But it's definitely carbon.
Mm,
That
so
tells me
it's
stuff.
6
So that's
protons.
gonna be 6 there,
And that'll be 7 on nitrogen,
and it's gonna be 7 here, and what goes down here and down here?
8 on the carbon, and 7.
This is also even, and this is magic. P is 7, that's in the 1p½ state, one of them. N equals 7, that's in 1p½, one there. And I think all I was trying to do is to see if I could see anything that really stuck out to me about carbon 14 and nitrogen. I mean, nitrogen's weird because it's 7-7, it's an odd-odd pairing. It shouldn't be that stable, but it's crazy stable. So there's something about 7. But anyway, nothing came to me, right? 10 to the minus 62, 10 to the minus 65. So for all I know is arithmetic. We're okay with this? I'm gonna erase stuff. All right. So let's just look at this decay. What did I not write?
The electron,
So
or
83 pluses, 82 pluses. Right?
Mhm.
So what do I need there? Definitely need a neutrino of some type.
Would that be a positron?
Yeah. If I'm reading this right, I got 83 protons, I've got 1 less proton and 1 extra neutron. So this went down. So then that's gotta go up, yeah. I need 83 plus charges on the right side. And so it basically converted a proton to a neutron. So one of these protons converted to a neutron and sent out that positron. That's relevant, so it may be, that's something to look at. I'm gonna do another example of decay.
Just so you know, 82 is lead and 84 is polonium.
In my answer. So maybe it's not polonium, maybe it's PB. Let me tell you the lifetimes I've got, and you can figure out whether that's simply a typo and I just happened to write down PO instead of PB. Because I got an electron, 83 goes down, proton goes down, so that's gotta show up. Where's polonium? Could it even potentially be correct?
It's on the, it would be.
So it'd be 84.
Yeah.
And that would be an electron over here. Beta minus, no. I definitely called it a beta minus decay. So it's not lead 82. It's polonium, but not 82, 84. Is that right? Yes, polonium is 84. So then the question is whether bismuth, I'll tell you that I got a half-life for this. I got a half-life of 5.012 days and an energy of 1.426 mega electron volts. So what you could do is see if that really is the decay of bismuth to polonium, or if that's going to resolve what I did there. And if this is a beta minus decay, then I don't know what happened with that. Beta plus decay is different, and I'm going to talk about that when I do the Dunlap example. The F, the value of F depends on whether you have an electron coming out or a proton coming out. And it depends on the Z of the nucleus. It depends on how much charge is in there. That interaction is changed by what's interacting. Okay, so we have an electron and an anti-electron neutrino. And so if I have those, plus a neutrino, and I know the electron is spin 1/2, and I know the neutrino has to have spin 1/2, what are my options?
0 and 1.
0 and 1. If they add up and give me 0, that's called Fermi decay. And if they add up and give me 1, that's called Gamow Teller. Named after the people who worked on it. They get their name wrong. If these two spins add together and give you 0, there's only one way to do that, so that's called a singlet state. To add to 1, there's 3 ways to do that, so that's called a triplet state. And if you know about singlets and triplets in atomic states, that's the same thing.
Is that like on an NMR kind of singlet and triplet?
Yep. Maybe not, because I think they may mean whether you have just one line or that. Do you know? Because you're doing NMR right now, and I don't know whether those come from these kind of singlet and triplet states. But it makes sense because there's only one way to do this and there's 3 ways to do this. There's only one way to get that transition, there's only 3 ways to get that. So yeah, that could well be. That would be worth asking Dr. Foggy about. If the singlet
I'm
and
just
triplet
not sure about the other.
lines. Yeah, it won't be this, right? It won't have
Yeah.
anything to do with Fermi or Gamow Teller. But it will be, if I have 2 electrons, do they combine into a singlet state? There's only one way to do it, or do they combine into a triplet state? There's 3 ways to do it. And those 3 will have different magnetic energies.
Mm-hmm.
But I don't know if that's where they come from. So, what this tells us is that the spin angular momentum has to be between the difference and and the sum because this angular momentum is either taken from or given to. So that's the parent nucleus and that's the daughter nucleus. I don't know why. I don't know why it's not parent and child, or mother and daughter, or father and son, or whatever, but it's parent and daughter. And so here, parent, daughter. And so you look at those states and you can figure out where we are in here. If they differ by 1, well, I didn't calculate those. I guess one thing to note is that if JD and JP are both 0, if they have 0 orbital angular momentum, there's only one kind of decay that can happen, Fermi decay. And there are a set of what are called allowed. If you look on, I'm going to say more about this in a later example. But there are allowed and forbidden decays. And one thing to learn about physics is that things that are allowed are very, very likely. Things that are forbidden are just not as likely. They're not forbidden, they're just discouraged. And it has to do with doing those integrals of the wave functions. So if these were both 0, then it's for sure that you're going to have Fermi decay. The only way to get gamma-Teller decay is if you can somehow get 1 in between these two values. And so that sort of tells you what can and cannot happen. I want to talk about parity violation. So we talked about how if they had different parities, that integral ought to be 0 and that shouldn't happen. And so 2 guys named Yang and Mills worked out a theory that said maybe it could be violated. It'd be interesting to look at that. And so somebody named Wu did the experiment and said, sure enough, look at that. Parity is violated. So there is something going on there that integral, which should be 0, isn't strictly 0. There is a parity violation. We'll talk a little bit about what that means. Basically, it means that neutrinos, their spin and their direction have a definite pattern. They always go in exactly the same direction related to their spin. And I'll try to make that make sense. Called their helicity. If you think about it, if something's spinning that way and it's going that way, it's kind of like it's making a helix, right? And you can be right-handed or left-handed according to whether your angular momentum is with your V or against your V. And so we're going to talk about what that means and what it tells us by looking at that. What's interesting is to note that Li and Yang got a Nobel Prize. Wu, who showed that it wasn't just a numerical game that they were playing on paper, got nothing. They eventually gave her, I don't think that's an accident, a Wolf Prize, because, it's the same thing. So anyway, yet one more. So let's talk about parity decay. It means we got to think about NMR, not really, but we need to think about whether or not you have magnetic dipoles pointing with the field or against the field. That's really the question they're going to talk about. And if I can align them, if I can get all my atoms lined up with the field, then I'll know which direction the magnetic field points. I'll know which way I know the direction of J, I always know that. I will know the direction of the angular momentum of the parent nucleus. And that sets a direction in space. Now I can look for where the electrons come from. And if they come from anywhere, then nothing to see here. If they're preferentially sent in one direction as opposed to the other, then that matters. Right now we've got something interesting, and I'll say more about that as we go. But we need to talk about, well, compared to the experiment that they did. I pretty much did this differently no matter what, depending on the day. Or it should be a J.
You got the numbers switched up again.
What goes where?
The total nucleons should be in the upper right.
6, what goes here?
The
27?
protons. Yeah.
60. Which is the spin of the electron neutrino pair.
1 plus.
Gotta be 1, right? The plus, what's that plus telling you? Anybody remember?
Spin up.
That was the parity. That's the total angular momentum, that's J. I don't know why I wrote I. I probably copied it from another paper somewhere. But that's the angular momentum. And this one is 5, this one is 4. That S has to be 1, so they are in the triplet S equals 1 state. So now I want to talk about the fraction that are pointing with the field. In your NMR, what fraction are pointed with or against the field? When you do NMR. Did they ever talk about that?
I know that like there's a alpha portion with and then like a beta portion against. Like,
Okay,
whenever
so
you apply
they
the field,
just
but
call it a fraction?
Mhm.
They never talked about that?
Not that I know of.
Okay, so I'm gonna talk a little bit about it. It has to do with thermodynamics, and I'm not gonna do the thermodynamics, so if you've had thermo, you should recognize this, and if you haven't, then know it's in your future. So, I've got a total of N magnetic poles, right? These are your protons in your NMR. In this case, these are my cobalt atom. And I need to create a preferred direction. I need them to be mostly oriented along one direction so that I can tell if they're pointing in random directions and the electrons come out in random directions, then of course they do, right? They could have a strong preference, but because the dipoles are randomly oriented, they're gonna come out in random directions. So I need to align them, so they need to be mostly up. So, if I write that as the number with the field minus the number against the field, that's going to be the total number times e to the minus mu b over kt. So the mu b you ought to recognize. Mu times b is the magnetic dipole moment times the strength of the magnetic field. Who knows what KT is? That's what T is.
Temperature.
T is the temperature, so KT, I'm really just converting temperature to joules. It really is just a conversion factor between temperature and joules. So, if I'm at this temperature, then on average I have this much energy, KT. I have KT energy. In room temperature, that's like 25 MeVs, 25 millielectron volts. It's a pretty small number. So what does that look like? I know. I'm not gonna write the Z, I'm gonna hold that thought. And I'm also gonna change this to that number divided by the total number. Delta N over the total number. This is the number with the field. As this temperature gets higher and higher and higher, that number will get smaller and smaller and smaller. The number with the field will get smaller as you raise the temperature. Those against the field, as you raise the temperature, more and more of them will be allowed to be against the field. Because what keeps them with the field, that's the torque created by the magnetic field. Magnetic field twists them around till they point. And if that's the only game in town, then they will all point with the field. Temperature, collisions from the other guys is what's banging them and forcing them to point against the field. When the temperature is really, really high, then they're as likely as not to be pointed with the field. That's the fractional ends cancel. That's something called the hyperbolic tangent. I'm putting some numbers in a second, but the main thing I want you to see out of that is that the strength of your field, the strength of that dipole, and the temperature dictate what that looks like. So that function starts off here at 0. And as my B, mu B over KT gets bigger, it rotates, flattens out to 1. That's just hyperbolic tangent of X, and that's what it looks like. And this is just the name for this weird function of exponentials. Tell me where the temperature is high, tell me where the temperature is low.
Temperature is high on the right.
Temperature is high on that side. T gets big. Yeah, that gets smaller, right? So T increases that way. This is me getting higher and higher temperature. So low temperatures, this is 1. How can this be 1? Is it everybody's with the field? If everybody's with the field, then N up will be N, divided by N, that'll be 1. Everybody's with the field at low temperatures over there. That's what that's telling me. As I raise the temperature, this is going down. As I raise the temperature, what's happening? More and more of them can point against the field. These numbers are close to the same. They're never quite the same, but they're really close to the same. And this number is getting closer and closer to 0. It only gets to 0 at infinite temperature, but room temperature is pretty hot. So your room temperature NMR, almost everybody, there's only a tiny, tiny, tiny amount that are with the field in excess of against the field. So let me say that better. The number that are with the field is bigger than the ones that are against the field, but only slightly, only by a really small amount. So you're looking, and that's why it's such a big deal to increase that field, because if I make this number bigger, then I can go to then this number gets bigger and I'm further along that graph. I'm getting closer to that difference. That's why 200, 400, I don't know how high they go, but whatever that megahertz are. Megahertz are how big is your magnetic field. That's really what it is. So, to do this experiment, I need to be down here. don't know what I said. I want to be out here where most of my states are in this with the field. I don't know what I said a second ago. I want to be out here. I want to be at low temperature, so I'm far out here. How far down do I need to be? I need for the temperature to be much, much less than UB over K. Small, big. That is something like 10 to the minus 23 joules per Tesla. That's the magnetic dipole moment of these nuclei. Ballpark. I picked a 1 Tesla field because you don't have to work hard to get a 1 Tesla field. If you want a 5 Tesla field, you gotta work. I'm not sure what the record is anymore, but it used to be, I think it was 80. It was like the world record. I don't know if that's what it is now, but getting a big magnetic field can be tough. And more to the point, getting it big enough to put your sample in and having it be uniform over that range, that can be hard. So I just used 1 Tesla. That's 10 to the minus 23 joules per Kelvin. Joules cancel, Tesla cancels, Kelvin comes on top, and that turns out to be just 1. That's negligible. So you basically need to be well below 1 Kelvin to do this experiment. You want all of these to be lined up with the field so that you have a preferred direction. You know what the orientation of your angular momentum is. So you know that your S is going to be along that line. J of your parent, J of your daughter, this has got to be oriented along that same axis. Now, if they're randomly oriented, then S will be randomly oriented. But if they have a preferred orientation because you're at this low temperature, then S will have that same orientation. And you can look for electrons going just this way or any direction. That's how that shows you parity decay. We know that mu is something like Q over mL. For electrons, there's no 2. I did that on the exam, right? You take mu for an electron and L for an electron, the ratio is Q over M, not Q over 2M. So that's something that we found on the test. But it tells you that mu and L are parallel to one another. They point along the same axis. Now I want to know next time what the parity operator, we're going to talk a little bit specifically about the parity operator and see what happens if I apply the parity operator to my momentum operator, which involves derivatives. I'm going to apply a parity operator to an angular momentum. See what this weird mirror image does. How does it affect P? How does it affect L? And what can we say about what ought to happen? Again, the goal is to understand what's the big deal about parity violation and what does it tell us about neutrinos.